Yeah, okay. So I've started recording. So let's start from where we have left last time. So quickly recall, what did we do last time in our first lecture? We did absolute values on a field, and we defined the notion of equivalence of absolute values. And assuming that the field is locally compact, we showed that on a finite dimensional vector space over it, any two norms are equivalent. And in particular, if you have a finite extension of such a field, then there is a unique extension of the absolute value if the extension exists. Okay, this is what we did first. And then what did we do? We proved this, we proved a named theorem, right? Art in vapors. It's an approximation theorem, so we proved that. And if you remember, I said this is analogous to the Chinese remainder theorem. And then maybe we stated Hensel's lemma and Krasnod's lemma. Both of this we will prove today. So today, that's all that we will do. We will prove these two results, Hensel and Krasnodar. So let me start sharing the screen. Yeah, after the update, MS Teams looks very different. Yeah, let me share the screen. So please confirm whether you can see the screen.
Yes.
So what you see is MS Teams only, no? Manu, maybe you want to, are you using an earphone or something? It's not always very audible what you say.
Yeah, I am using your phone.
So now it's better. So now maybe you have removed it, right?
No, I just got the mouthpiece close to my mouth.
Okay, okay. So when you are asking something, you please do that. Otherwise, I can't hear you.
Okay.
So, okay, so this is what you see. One second. I'm a bit confused today with the settings. So, I guess if I just project lecture 2, it should come. And yeah, you can see, right? You can see the slides, no?
Yes.
Yeah, okay. So let's continue. So today we will do, I mean, I have already stated Hensel's lemma and Krasnod's lemma last time. Today we will prove it. By the way, Hensel's lemma, there are so many various versions. So I'm following Lang, and some are better for some particular applications. So I will do what is there in Lang's book. Okay, so once again, last time we discussed absolute values on a field, and we saw that if E over K is a finite extension, then an extension of an absolute value on K to E is uniquely determined if it exists, and where K is assumed to be complete with respect to the absolute value. This is true generally for any complete field, but our proof assumes that K is locally compact, and you can check a locally compact field is automatically complete. So this you can check, and so if the absolute value is discrete, then in fact, so here I said if it exists, it's unique. If you have a discrete absolute value, you can certainly extend it. So what you can do is, if you have a discrete absolute value on K, then to E you can extend it via the norm map from E to K. So you can define absolute value on E to B. You take the norm, come down, and in order to make it an extension, I mean to agree on the base field, you take the correct power, 1 by the degree of E over K. So it's not obvious that this is an absolute value, right? Triangle inequality you need to check. So you check, I mean, our ultrametric inequality you need to check. So you check this, that this is an absolute value. By the way, throughout the slides, there will be certain points which I leave it for you to check. Please do check. If you're serious about the course, you should check these small things that I'm asking you to do. Some of these I might have checked and I would like you to check. Some of these I myself might not have checked recently. So if you find anything wrong or anything difficult, let me know. You can message me or you can email me. Yeah, then I will also check. So check that this is, so use the fact that it's a discrete valuation in order to get this extension. Okay, so there's a small check to be done. And then in the last class, we proved this approximation theorem. It's called usually called the weak approximation theorem, and this is due to Artin and Vapers, Emil Artin and George Vapers. And we said that this is analogous to the Chinese remainder theorem. What I did not mention last time, which let me quickly mention, let's do it over rational numbers. In certain situations with discrete valuation, actually Chinese remainder theorem will prove this approximation theorem. Let's just do quickly for Q, rational numbers. So suppose, so in Artin Vapers, finitely many absolute values. Yeah.
Discrete absolute value means the image is in Z.
Images discrete, images Z, yes.
Okay.
Yeah. Yeah, that's the meaning of that. Yeah. So, in Q, if you take the valuations given by prime numbers, then of course it's discrete, right? The absolute value will be C power C we took as 1 by P power R, and that R is an integer. So valuation meaning that R. So it is discrete. And the image of the valuation is discrete. The absolute value will be C power R. That R is discrete. R is from Z. So, so suppose you are in Q and all the finitely many absolute values are discrete. The periodic absolute values, no Archimedean absolute value. We are not taking the usual modulus. Then given by prime numbers. Then this Artin-Vapers result actually you can get it using Chinese remainder theorem. How? Because in Artin-Vapers, what is given to you? Finitely many numbers, right? Finitely many xi's are given, and you want to get an x such that mod x minus xi, the ith absolute value is less than epsilon. Whatever epsilon you have to choose an x. You can make this sufficiently small. So how do you do this? So xi's are given to you. So these are some finitely many rational numbers. Take the common denominator d and consider dxi. So dxi will be in z for each I. Now you can apply the Chinese remainder theorem to these finitely many prime numbers pi. You can in fact apply to pi power ni for whatever ni you want, right? The ideals generated by powers of different primes will be co-maximal. So you can apply Chinese remainder theorem and you can solve for an x in z. You can get an x in z such that x is congruent to dxi mod pi power ni, and this is true for any ni. So what's the meaning of that? If you take x minus dxi, there's a power of it has a factor of pi power ni. So the pi absolute value is very small. As ni is bigger and bigger, you can make this small. So x minus dxi you can make arbitrarily small by choosing ni bigger and bigger. This is Chinese remainder theorem. So in particular, x by d in Q is near to xi for each I. You agree? X minus dxi can be made arbitrarily small. So x by d minus xi can be made arbitrarily small. And that's what you wanted. So we proved the general result where we don't assume discrete or anything. This is true for any absolute value. In the discrete case, in this example, it follows from Chinese remainder theorem. And the exact same argument. So a bit later, we will do number fields in general. So what's a number field? A number field by definition is a finite extension of Q. Okay, this is the definition of a number field. A finite extension of the field of rational numbers is called a number field. And the argument generalizes. There is what is called the ring of integers, which we will define later. And K is the quotient field of the ring of integers. And therefore, this idea of taking common denominator and applying Chinese remainder theorem, all that will go through. So this argument generalizes the object analogous to Z. So what is Z for Q? There is a similar object in any number field, any finite extension of K, and that is called the ring of integers of K. We will do it later, but it's easy to say. So just like, all of you know what an algebraic number is, right? What is an algebraic number? An algebraic number is a complex number that satisfies a monic polynomial with coefficients in Q. And there is a notion of an algebraic integer, which is a complex number which satisfies a monic polynomial with coefficients in Z. Earlier coefficients in Q, algebraic number, algebraic integer, coefficients in Z. So, and then you have the notion of, if you have Z is contained in Q, and if you take a finite extension here, you can talk about the integral closure of Z in that K. So these will be all the elements of K which are algebraic integers. Yeah, elements of K which are algebraic integers. So that will be the ring of integers. Anyway, we will do this more formally soon. So this is typically denoted by OK in Lang. Okay, so the same argument goes through. So Chinese remainder theorem will do it for discrete valuations. Now let's restate Hensel's lemma. So I stated this last time. So fx is a polynomial. Coefficients are from. So what is the situation here? We are assuming that k has an absolute value with respect to which it is a complete field. That's a starting assumption. And you recall I defined O. So you have this absolute value. And what was the definition of O? Can someone quickly recall? Can one of you recall what's the definition of O? Yeah, we have an absolute value, and how did we define O?
Sir, I think it was a PID with one maximal ideal.
Yeah, but we had a definition, no? What is given
It
to you
was
K
x,
and
x
just an
belong to K such that absolute value of x is less equal 1.
correct. That was the definition. And then if you take strictly less than 1, that's a unique maximal ideal. Yeah. So that is true. Yeah. So I didn't say PID or anything, no? I don't think I said that. It's just, so O is just modulus is less than or equal to 1. Okay, so that's the ring of integers by definition, and f has coefficients from O, and what is given to you is one element from O, and that satisfies this inequality. Modulus of f of alpha naught is strictly less than modulus of f prime alpha naught square, where f prime is formal derivative. Just take term by term derivative. If this is true, then there is this algorithm. You can construct this sequence starting with alpha naught, alpha 1, alpha 2, etc. Construct like this. You remember this, right? This is where I got a doubt and I went to Google and Google something, etc. last time. So this sequence converges to a root of f of x, and moreover this root belongs to O, the ring of integers. So you have a method of constructing roots, and you remember we did an example also, right? I think we showed that x square plus 7 has a root in Q2, the field of two-adic integers, right? This we did last time. So moreover, you can bound the distance of this final root alpha from alpha naught. This is bounded by f of alpha naught by f prime alpha naught square. And this is strictly less than 1. That is a condition that's given to you. So let's prove this today. One remark is that, so this is fine, but if you just take this identity, it's possible that there are more than one alpha which satisfy this identity. Of course, I'm not talking about Hensel's lemma now. I'm making another remark that such an identity could be satisfied by more than one alpha. But in fact, you can have a stronger version of Hensel's lemma where without the square here, this inequality is satisfied, and then there is a unique alpha satisfying this kind of this inequality. So I haven't seen the proof, but the proof is there in another book, Local Fields by Cassels. And by the way, James Milne has a wonderful set of notes on algebraic number theory, which is there on the internet for free. And I got this reference from there. So page 121 of Milne's notes. Okay. Anyway, that's an extra remark. So let's prove Hensel's lemma. So this is the starting point. This number, absolute value of this quantity, let me call it C, and we know that this is strictly less than 1. And we are going to make 3 claims now, and we will prove it by induction. One is that mod alpha I is less than or equal to 1. So you remember last time I made this quick remark that I'm not saying anything about the alpha i's. I'm only saying alpha naught belongs to O, and then I'm saying that the final root belongs to O, and I said I'm not making any claim about the alpha i's, but if you look at the proof, I'm actually claiming that each of the alpha I also belongs to O. That's my first claim. Okay, so though the statement doesn't say anything, the proof also makes it clear that each of these numbers modulus is less than or equal to 1. In other words, each of this alpha I belongs to O. And the second claim is that each of this alpha I, the distance from alpha naught, is less than or equal to this. What was Hensel's lemma saying? The final alpha that you get has this property that alpha minus alpha naught is less than or equal to C. We are claiming this for each of the alpha i's that we are constructing algorithmically. And the third statement is f of alpha I by f prime of alpha I square, the modulus, is less than or equal to C power 2 power I. Okay, so we are going to make these 3 claims, and suppose we have proved these 3 claims. Okay, we are going to prove this by induction. When I equal to 0, all these things are okay, no? Do you agree that when I equal to 0, these things are true? Can one of you tell me? Yeah? The thing is, on this slide, I cannot see who's speaking. Yeah. Please
Yes,
do.
yes.
Yeah. So, Manav, you are saying that I equal to 0, it's obvious?
Yeah, it follows directly, I mean, from the
Because that is what is
information.
given to you, right? I equal to 0, alpha naught is an algebraic integer is given to you. Alpha naught minus alpha naught is 0. So 0 is of course less than or equal to C. And this condition is given to you. F of alpha naught by f prime alpha naught square is less than or equal to this. So induction can start, and we will prove this using induction soon. But now assume the claim. If you assume this claim, then I'm going to say that Hensel's lemma is done. You are going to get an alpha. So what I'm going to show is that this alpha I, the sequence that you have got, is convergent. And suppose it converges and you take the limit to be alpha, then is it true that all the statements are correct? So each of the alpha I modulus is less than or equal to 1. Therefore, that property is true for the limit also. Therefore, alpha belongs to O. And each of the alpha I has this bound. So the limit also has that bound. So this is also fine. And f of alpha I by f prime alpha I square is becoming smaller and smaller. And therefore, in the limit, f of alpha will be 0, right? As I becomes, as you proceed along this sequence, this is getting smaller and smaller because C is less than 1, right? So C power 2 power I is getting smaller and smaller. So in the limit, f of alpha is 0, establishing that alpha is a root. So what do you need to show to prove Hensel's lemma? If you assume this claim, you have to show that the sequence converges. And the sequence converges, we are going to show by showing that the sequence is Cauchy. That's enough, no? Why is it enough to show that the sequence is Cauchy?
Because K is complete.
Because K is complete. So we are going to show that it is Cauchy. So by 1, this property, assume the claim. So we are assuming that all the alpha i's have this property. So mod alpha is less than or equal to 1, meaning alpha I belongs to O. Therefore, you can conclude that G of alpha I belongs to O for any Gx in OX. Why is that? Because G has coefficients in O. So G of alpha I will be sums and products of elements from O, because alpha is in O, and therefore G of alpha is in O, because O is a ring. So if you have an element there and if the coefficients are there, then various products and sums, all of them are in O. And in particular, I will be applying this to f prime. So we know that f prime of alpha I, the modulus is less than or equal to 1. Okay. And this is the definition of alpha I plus 1. Algorithmically, this is how it is defined. And therefore, alpha I plus 1 minus alpha I, what can you say? This difference, the modulus is modulus of f of alpha I by f prime alpha I. And do you agree with the next statement? Can you tell me why this is true? So this is just from the earlier thing, and I am making this claim. Modulus of f of alpha I by f prime alpha I is less than or equal to modulus of f of alpha I by f prime alpha I square. Why is that true?
Because modulus of f prime alpha is less than equal to 1.
Correct, because of this. Yeah, therefore this is true, and this is less than or equal to, you are assuming the claim. So this is less than or equal to c power 2 power I. Fine, c power 2 power I. So this particular thing tells you that, so this is what we just proved, alpha I plus 1 minus alpha I modulus is less than or equal to c power 2 power I, and I'm going to make this claim that therefore alpha I is Cauchy. Does this look okay? Why? What is the definition of a sequence being Cauchy?
For every epsilon greater than 0, there exists an n naught such that for all m and n greater than or equal to n naught, alpha am minus an mod of that is less than epsilon.
Absolutely. Right? You are right. So it is for each m and n above a certain stage, whereas I am showing it only for the successive indices I plus 1 and I. Is that enough in general? Is this true in real analysis that such a thing is true? If you can make successive differences small, should it necessarily be Cauchy?
No.
No.
1 by yeah.
That is not true. But here it is true. Why? Because our absolute value is non-Archimedean. So if you have successive differences arbitrarily small, then beyond a stage, then any difference is arbitrarily small, because if you have am minus an, suppose m is bigger than n, am minus an, you can write this as am minus 1 plus am minus 1 minus am minus 2, etc. a finite sum, and that modulus is less than or equal to maximum of the successive differences. So if the successive differences are arbitrarily small, then for any m and n, am minus an, the modulus is arbitrarily small. So this is enough in the non-Archimedean situation. So analysis is simpler in the non-Archimedean situation than in the Archimedean situation. For example, showing something as Cauchy is easier. Agreed, no? So that's the proof that implies this is Cauchy. Therefore, it converges to some alpha because you are assuming that K is complete. And in fact, alpha belongs to O. Why? Because if alpha is in K and alpha is the limit, so each alpha I modulus is less than or equal to 1. Therefore, mod alpha is also less than or equal to 1. And f of alpha is 0 by the third condition, because f of alpha I by something is getting arbitrarily small. So f of alpha will be 0. And alpha minus alpha naught is less than or equal to c, because this condition is true for each alpha I by 2. So everything is done if you have proved the claim. So now we prove the claim by induction. As Manav noticed, when I equal to 0, it's all obvious. So you can assume up to I, and you have to prove for I plus 1. Okay, so let's start. So up to I have assumed. So this is given to me. Well, this we proved, right? Assuming the claim, you can prove this. So this is given to you. And now we have to prove that mod alpha I plus 1 is less than or equal to 1. But that's easy because it's less than or equal to maximum of this difference and mod alpha I. this is less than or equal to this, which is strictly less than 1, and this is also less than or equal to 1. So both are less than or equal to 1, therefore that's less than or equal to 1. So the first claim is true. Second claim is mod of alpha I plus 1 minus alpha naught is less than or equal to C, or strictly less than C maybe. No, less than or equal to C, and this also follows easily because this is less than or equal to maximum of alpha I plus 1 minus alpha I and alpha I minus alpha naught. By induction hypothesis, this is less than or equal to C, and we have proved that this is less than or equal to C power 2 power I, which is of course less than or equal to C because C is less than 1. So both are less than or equal to C, therefore this is less than or equal to C. In fact, this is equal to C. Yeah, this maximum is C because this is C and this is something strictly less than C. No, I shouldn't say equal to C. I should only say less than or equal to C. This is a typo, right? Because what I know is this is less than or equal to C power 2 power I, which is less than or equal to C. And what I know is this is less than or equal to C. So this is a typo. I will change it after the class. This is less than or equal to C, which is what we wanted. Finally, what do we have to show? We have to show claim number 3. Claim number 3 is that f of alpha I by f prime alpha I square, that modulus is less than or equal to C power 2 power I. So we have to show this for I plus 1. Okay. So if you take this polynomial, f is the given polynomial, and suppose you have, some a and some a is some constant and x is your variable. So if you call that gx and if you expand that polynomial using its Taylor expansion, I mean, no need of Taylor expansion. Algebraically, you can do this, right? It's just a polynomial, but anyway, you know this. Its expansion will be, so I'm expanding gx. So gx will be g of 0. I'm expanding at 0. So it will be g of 0 plus g prime 0 x plus g double prime 0 by 2 x square plus etc. And I have written it in terms of a. Okay, so you get this expansion, and now because it's a polynomial, you know that these coefficients are actually in your ring O, right? Because f has coefficients in O and it's a polynomial with coefficients in O. So all these fractions are actually in O because it's a polynomial. Okay. Now I'm going to apply this a minus x. A will be alpha I plus 1. No, a will be alpha I and x will be whatever is our algorithm, right? So my algorithm is this one. So I will take a to be alpha I and x to be this fraction, f of alpha I by f prime alpha I. A is this, x is this, so a minus x is alpha I plus 1. So if you plug in there, what will you get? You will get f of alpha I plus 1. Why is that? Because this is alpha I and this is f of alpha I by f prime alpha I. So that difference is alpha I plus 1. A is alpha I, so this is f alpha I minus f prime at alpha I and x is f alpha I by f prime alpha I plus these things. So I am taking x square common. X square is this, that is common. And what remains, if x square is common, what remains is f double prime a by 2 minus f3a by 6 times x plus etc. But all those things belong to your ring of integers O. Right? All these coefficients are anyway from O because it's a polynomial with coefficients in O. And x is also in O. Why is x in O? Because this one is in O, right? Because modulus of this is less than or equal to modulus of f of alpha I by f prime alpha I square, and that is less than 1. So this is also in O. Therefore, what you can say is if you take x square as common, remaining thing beta is from O. So this you claim. This is obvious. Okay. So you get this expansion and this cancels. No, f prime alpha I goes with this. So this goes away. This is just 0. So what you are getting is f of alpha I plus 1 is something in O times this square. Therefore, modulus of f of alpha I plus 1 is less than or equal to modulus of this square because modulus of beta is less than or equal to 1 and this goes away. So you conclude this. This is the first conclusion. And one more claim you make, again the same idea, use Taylor expansion, but for this polynomial, f prime of a minus x. Earlier you applied it to f of a minus x. If you apply it to f prime of a minus x, I'm expanding hx as h of 0 plus h prime 0 plus etc. So if you do that, you will get h of 0, which is f prime of a. Then h prime at 0 will be f double prime minus of f double prime a times x. Then the next thing will be plus f triple prime a by 2 times x square plus etc. Again, exactly like last time, you can conclude that this whatever is in bracket is from O. Exactly like in the last step. So if the bracket thing is in O, what is the absolute value of this much? It is mod x, right? Because it is less than or equal to mod x. Because the bracket has absolute value less than or equal to 1. So this highlighted part has absolute value less than or equal to mod x. And how do you compare mod x with mod f prime a? So remember, x is this. So mod x is this. And the claim is mod x is strictly less than mod of f prime a. Why is that? Why is this true? This is our this we have already this is our induction hypothesis, right? Induction hypothesis tells you that up to I you have claim 1, claim 2, claim 3. And what was claim 3? Claim 3 is f of alpha I by f prime of alpha I square, that is less than or equal to c power 2 power I. And c is less than 1. So c power 2 power I is less than 1. So f of alpha I by f prime of alpha I square is less than 1. So that means this, no? So this you have. So in this identity, what you are getting is modulus of this is strictly less than modulus of this. So what can you say about modulus of this? It will be less than or equal to maximum of modulus of this and modulus of this, and that maximum is this. Maximum is this. Therefore, you see that modulus of f prime of alpha I plus 1, I am taking a to be alpha I and x to be f of alpha I by f prime alpha I. So this is alpha I plus 1. That modulus is equal to modulus of f prime a, which is modulus of f prime alpha I. Is this step clear to all of you? Yeah, is this step okay? Manav, is that okay to you?
So can you go back to the slide for a minute?
Yeah,
I didn't follow the last step, and I was just looking at it.
Yeah. So which step? This one is okay?
Yeah, that's fine.
This one is okay. And then I'm making this claim that these belong to O. That is because, all these, see, fraction only you have to worry, but fractions will be, these are expansion of a polynomial with coefficients in O. So these fractions also will be in O. So this part is in O. So the modulus of this term is less than or equal to modulus of x. But x is f of alpha I by f prime alpha I. So this is modulus of x. And I am saying that that is strictly less than modulus of f prime a. A is alpha I. So this is the claim, but this is equivalent to saying modulus of f of alpha I by f prime of alpha I square is strictly less than 1, right?
Yeah, that is true.
Yeah, and that is true because of our claim 3. By induction hypothesis, we have assumed this, no?
Yes.
And this is strictly less than 1, right? Because C is strictly less than 1. Yeah, okay, Manav?
Yes.
Yes. So therefore, when you say less than or equal to maximum of the two, less than or equal to maximum of the two, where are we? Yeah, here. You agree with this now? So f prime at alpha I plus 1 is less than or equal to, yeah, no, good that you had a doubt, because I had to make one more thing. So f prime of this, the modulus is less than or equal to maximum of modulus of this, comma modulus of this, which is this. So one more thing that I need to say is, yeah, I'm saying this inequality, right? I'm not saying it's less than. So Manav, if this was less than or equal to, then you have no confusion, right?
Yeah, then it's fine.
Then it's fine. Your confusion is about equality, right?
Yes.
Yeah. So what I need to say is, in our ultrametric inequality, so what is our inequality? Mod x plus y is less than or equal to maximum of mod x comma mod y, right? And I should say that when mod x is not equal to mod y, the inequality is actually an equality. So the ultrametric inequality is mod x plus y is less than or equal to maximum of mod x comma mod y. And I'm making one more claim that if mod x is not equal to mod y, right, maximum of two things, mod x comma mod y, if mod x is not equal to mod y, then that inequality is actually an equality. Okay, so that is part of my, let's take that as part of my definition. For example, the absolute values that we will deal with, this is true. For example, the periodic absolute value you can check. So have you checked earlier that periodic absolute value is indeed an absolute value? So if you are checking that, you will see that when two things have different absolute value, the inequality is actually an equality. So good. So I will make a remark, somewhere I will type a note that we are using that fact. So that's how we are getting equality. And unknowingly, I was using it here while saying it's equal to, no, there it's anyway not true. This is less than or equal to C. So here it is indeed a typo, which I will change, less than or equal to C. But here there is no typo. But one thing I haven't clarified is I'm using something more than what I told you.
So, but Lang doesn't define the condition in that way.
Yeah, but we need that. We need that. I will add that as a note.
No, so does he do something different to prove this? I mean,
No. So, textbooks can have some small omissions. We need to add that. Yeah.
Okay.
This is Manav. Is this Manav?
Yes, yes.
Okay. So Manav, let's discuss this point since I didn't think about it before you asked. See, when we axiomatically define something, I cannot claim that automatically this follows, right? Or is it automatic? So one thing is to prove that this is true from the assumption. If mod x is not mod y, then I can show that it is actually equal from whatever assumptions are there. If we can do that, then we don't need to do anything. You agree, no?
Yes.
Yeah. So that's one option. We will, take the correct option, and only after that I will upload this on Moodle. So we will try to prove that. If not, I will add it as a remark. That's part of my definition. So since, as you said, Lang doesn't mention it, maybe it's possible to prove it. So quickly, if mod x plus y is less than or equal to maximum of mod x mod y is our assumption, and suppose mod x is not mod y. Suppose mod x is not mod y. Then we can prove that it's an equality, no? Because you can write x as x minus y plus y, right? You write x as x minus y plus y and apply the same thing to mod x. What will you get? You will get mod x is less than or equal to maximum of mod x minus y comma mod y. Right? And
Yes.
What was our assumption? Mod x is not equal to mod y. So mod x is not equal to mod y. We can, without loss of generality, assume that one is bigger than the other, right? So let's assume that mod x is strictly bigger than mod y. So what can you conclude from this inequality? Mod x is less than or equal to maximum of mod x minus y comma mod y. And mod x is bigger than mod y. So that tells you that mod x minus y equal to mod x, no? If you
mod
have a
x minus y greater than equal to mod x. Mod x minus y greater than equal to. Okay, yeah, equal to mod x.
Equal to mod x, right? So that's all that we needed to show. X minus y, x plus y doesn't matter.
Yeah, okay.
So it follows. That's why Lang doesn't mention anything, and I don't have to add any note. Maybe I will add a note that this follows. But anyway, you have understood, right?
Yes.
Yeah, it is one such argument. I think maybe our argument is already complete. Otherwise, some such argument you have to give. Okay.
No, it is complete.
It is complete. Okay. So I'm not that quick, and when I talk without having thought about it just before, I always get a bit of a doubt. Anyway, in my chair, I have to be a bit more careful. So okay. So if you confirm, fine. Anyway, I will think about it once again and we'll put the argument down. Okay. So now you're fine with this. Right?
Yes.
Now you're fine with this. And now see the crucial point. What do we have to show? We have to show that this quantity, is less than or equal to what? C power 2
C power 2 power I plus 1.
I plus 1, right? Now it follows because you have this inequality here and this identity here. So we will make use of both of that. So this is equal to f of alpha I plus 1 by f prime alpha I square. Why? Because f prime alpha I plus 1 modulus is same as f prime alpha I modulus. So I have changed I plus 1 to I. Now f of alpha I plus 1, I have this inequality. So plug that in. So I get f of alpha I by f prime alpha I square whole square. Right? This is less than or equal to f of alpha I square. So that is there by f prime alpha I square, and there is already an f prime alpha I square. So that is f prime alpha I power 4. Agree? And by induction hypothesis, this part is less than or equal to c power 2 power I and power 2. So that is c power 2 power I power 2, which is c power 2 power I plus 1. So we are done. So by induction, we have proved all the three claims, and we have already proved that if we prove the three claims, then Hensel's lemma follows. Agree? So this is a proof of Hensel's lemma as in Lang. There are some other formulations of Hensel's lemma, and there are stronger formulations also. But let's not do too much because we have to come back and do number fields and other things. Of course, this is an area in itself. There is an area called valuation theory where they study fields called Henselian fields, and Hensel's lemma is a research area in itself with much stronger conditions, stronger things. Maybe one or two I can state, and we will not get into the proof. So most of these stronger versions are apparently there in this book by Cassels, titled Local Fields. I haven't seen that book. Okay, so this remark I already mentioned in the last class. I said that the statement of Hensel's lemma needs alpha naught belongs to O. That was the starting hypothesis. And it asserts that alpha belongs to O. And I quickly said I am not making any claim about the intermediate alpha is. Maybe they are outside O. I did make this claim verbally. It was not part of my slides. As a statement goes, this is fine. But from the proof, I was wrong, right? I mean, in the sense the proof is claiming alpha I belongs to O. And that was the way we proved alpha belongs to O. So I just wanted to, clarify that. Whatever I said is still true. I mean, from the statement, we are not claiming anything about alpha i's, but the proof shows that each of the alpha I belongs to O. That is the way we show alpha itself belongs to O. So proof shows that each alpha I does belong to O. So something to remember about the proof. And here is one quick application. So what is this notation O star? Whenever you have a ring, if you put times, what does it mean?
Set of units.
Set of units. So suppose U is a unit in this O. So can you classify in terms of absolute value what will be a unit? Because you have an absolute value. So what will be the characterization of units?
We saw last time that the maximal ideal was the mod alpha less than 1, right? So
yeah,
it will be mod alpha equal to 1 set of units.
Correct. In fact, without that itself, you can say, I mean, in fact, you claim that that is a unique maximal ideal by knowing that outside it is units. So you have to give a proof that U is a unit, is saying mod U is 1. That you have to prove first. And that is easy because if U is a unit by definition, U inverse is also in your ring. right? That's the definition of a unit, no? So 1 equal to u times u inverse, take absolute value. So mod 1 is 1, which is mod u times mod u
and
inverse.
mod u inverse are less than equal to
1 mod u inverse is 1. So unit means modulus is 1, and therefore mod strictly less than 1 becomes your unique maximal ID because the complement consists of units. Yeah. So let u be a unit and consider this simple polynomial x power m minus u. Okay. And assume, suppose it is given to you that mod u minus 1 is less than mod m square, where m is the degree of the polynomial. Suppose this is given to you. Now this is a nice situation where you can apply Hensel's lemma, right? If you take alpha not equal to 1, if you take alpha not equal to 1, then what is this saying? This is what u minus 1 is what? It is modulus of f of 1. And what is modulus of f prime 1? What is f prime? F prime is m times x power m minus 1. This goes away. And f prime at 1 is m. So this condition, if this is given to you, this is exactly the condition in Hensel's lemma. F of 1 modulus is less than, strictly less than modulus of f prime 1 square. So what will Hensel's lemma say? If this condition is true, starting with 1, you can form that sequence and that will converge to a root of f. So you will get a sequence converging to a root of f. In particular, x power m minus u equal to 0 has a solution in the ring of integers. So there is an alpha such that alpha power m equal to u. So you can take u has an mth root in O. So if somehow you know this, then you have proved that u has an mth root in O. But this mth root in O, you can say that it's actually in O star, no? If alpha is such that alpha power m equal to u and u is a unit and alpha is in O, therefore alpha has to be a unit, right? Because mod alpha power m equal to 1, therefore mod alpha is 1. Agree? So it's obviously a unit. So certain units you can take mth roots, provided some such easy to verify things are there. Of course, throughout this proof I have assumed that the characteristic of k does not divide m. In my mind always I'm thinking of QP, so characteristic is 0. But if your field has positive characteristic, you have used the fact that characteristic doesn't divide m, because otherwise f prime x will be m x power m minus 1, which will be identically 0. So you will not get this condition. So here you have used this fact. Okay, all right. Let's come to Krasnodar's lemma. So Krasnodar,
you have not assumed that like the mod u minus 1 less than m square condition will never be satisfied if m is m characteristic of k divides m, right?
no, this is some condition only, no?
No, like mod m will be 0, right? If characteristic of k divides m.
If characteristic of k divides m, why do you
Then
say
m is 0, right? M is identically equal to 0 in k.
okay, fine. Yeah, m is yeah, after all I'm taking these elements from field, and m is equal to, yeah, that's correct. Yeah. So what I should say is if the characteristic doesn't divide m, then this kind of a method works, right? Because this such a condition will not be there if, as you said, if characteristic k is divisible by m. So all these things, so this condition you are getting only because characteristic doesn't divide m. Yes. So maybe I should have started by saying assume characteristic doesn't divide m and then write this. But anyway, the point is understood, right? Yeah. So yeah, you're right. So let's come to Krasnodar, and this also I stated last time, and I also said something about Krasnodar's lemma. No, I verbally said that there's not much in the proof, but it's very, very important. The proof is kind of there's not much going into the proof, other than one fact that we observed at the starting of the last class. But let's see the proof. But that doesn't say that because proof is easy, don't assume that the lemma is trivial. It's a very important lemma. It so happens that it has an easy proof. Okay, so K bar is an algebraic closure. Okay, fix an algebraic closure, and for alpha in K bar, we denote its Galois conjugates by alpha 2, etc. alpha n. So alpha 1 is alpha, and the rest of the Galois conjugates. So, so these are the other roots of the minimal polynomial of alpha. And let's assume that K bar has an absolute value mod, which will be there in most of our situations. For example, at the starting, I said if there is a discrete absolute value on K, then you can extend it using norm, and you will get an absolute value on any finite extension, and therefore on K bar. So if you start with an absolute value on K, and if it's a discrete absolute value, then on K bar you automatically have an absolute value, which is unique, right? Because extension of absolute value is unique whenever possible, and we know how to extend it if it is discrete, but I'm not assuming discrete. So let me anyway assume that there's an absolute value on K bar, and then Krasnodar lemma says if beta is an algebraic integer, beta algebraic number, beta is in K bar is such that mod beta minus alpha is strictly less than mod alpha I minus alpha. So if this is true, then what was the statement? Do you remember?
So just a question, are we still assuming that K is non-Archimedean and complete?
Yes. Throughout Hensel and Krasnodar, starting assumption. Yeah, so I did not repeat that assumption here, which was there in my last lecture slide. The assumption for all these things is K is non-Archimedean complete with an absolute value, and O is defined as mod less than or equal to 1. That's the assumption for all these polynomial results. Okay. So what is the conclusion of Krasnodar's lemma? Do you remember? This was the hypothesis. If beta is such that beta minus alpha is less than the distance between any of the conjugates and alpha, then there was a containment of fields, right? So the containment was K alpha is contained in K beta. This was Krasnodar's lemma. Okay. So maybe it's not so easy to remember, but the plain English is easier to remember. So the statement is that if alpha is closer to beta, 2 is missing, typo. If alpha is closer to beta than any of its conjugates, if alpha is closer to beta than any of its conjugates, then K alpha is contained in K beta. So this is Krasnodar's lemma. So let's prove this. Proof is easy. So if K has a discrete absolute value, then it has a unique extension to K bar, as we already mentioned, and I asked you to check something, so you should check it. This was the very first slide. Okay. So let's prove Krasnodar's lemma. For this, recall what we have shown last time, that if sigma is an isomorphism of E over K meaning sigma of x equal to x for each x in K, and sigma is a field morphism from E to its image inside E bar, inside K bar, the algebraic closure. Then what did we prove? We proved that mod of sigma alpha is mod of alpha. Why is that? Because if there is an extension of the absolute value, then the extension is unique. And if if you have extended, then mod sigma alpha gives you another extension. And therefore, these two should agree for each alpha in E. Remember, this we did last time, and this is all that I need to use in order to prove Krasnodar's lemma. So this was because extensions of absolute values are uniquely determined. So now let's come to Krasnodar's lemma. For the proof of Krasnodar's lemma, consider this extension. So you have two elements in the statement of lemma. There are only two elements, right? Alpha and beta, both are algebraic numbers. You're taking from the algebraic closure. No, the word algebraic number is not used here maybe, but both alpha and beta are algebraic over K. That's what I meant from the algebraic closure. And of course, K beta alpha contains K beta. There's a larger field. So consider this extension. And let tau be an isomorphism of K beta alpha over K beta. Okay, so from K beta alpha to its image, tau of K beta alpha, take a field isomorphism, which is over K beta. So tau fixes beta. Tau fixes anything in K beta. So take such a tau, and consider modulus of beta minus tau of alpha. Tau is this kind of an isomorphism of k beta alpha over k beta, and consider mod beta minus tau of alpha. But this is equal to tau of beta minus alpha. You agree? Because tau is a field morphism. So tau of beta minus alpha is tau of beta minus tau of alpha, and tau of beta is beta because it's fixing k beta. So this is same as this. And what is this? What is modulus of tau of beta minus alpha? This is same as modulus of beta minus alpha. Why? Why is that?
From the previous slide.
Because of the previous slide, mod sigma x is mod x for any sigma or isomorphism of the field over that. So because of the previous slide, this is this. So mod beta minus tau alpha is equal to mod beta minus alpha by the uniqueness of extension of absolute values. Therefore, modulus of tau alpha minus alpha, if you take, this is tau alpha minus beta plus beta minus alpha. This is less than or equal to maximum of tau alpha minus beta and beta minus alpha, but tau alpha minus beta and beta minus alpha absolute values are same. So that maximum is actually mod beta minus alpha. So this is less than or equal to mod beta minus alpha, and our hypothesis is that mod beta minus alpha is strictly less than mod alpha I minus alpha for each I. For each of the conjugate, this is the hypothesis that is given to you. So finally you are getting mod tau alpha minus alpha is strictly less than the distance between alpha and any of the other conjugates. So what is the conclusion? What is the conclusion from this strict inequality?
So isn't mod alpha minus alpha just equal to mod alpha? Because alpha is the Galois conjugate, right? So there is a endomorphism from endomorphism between the algebraic closures such that alpha goes to alpha I.
Yes. So you are saying that mod alpha is equal to mod alpha, right?
Yes.
Here you are saying mod alpha is equal to mod alpha. That's okay. That is true. That's not contradicting anything, no?
No, it's not contradicting, but just saying so then mod alpha I minus alpha just means mod alpha, right? Because it's less than equal to the maximum.
No. It is not
Okay,
mod
not
alpha.
equal. So less than equal to mod alpha. Yeah.
Yes. It is less than or equal to mod alpha. That is true. But it need not be equal because it can be much less. Because our equality was if the two things are distinct. Otherwise, it can crash down, come down.
Yeah.
Okay. And once again, you said mod alpha is mod alpha because they are Galois conjugates. Yes. Yeah. Good. So that's all correct. Whatever you said is correct. That is exactly this statement, no?
Yes.
Mod alpha is exactly this statement. That's correct. Yeah, that's correct. So mod alpha I minus alpha I minus alpha is strictly less than mod alpha. That is correct. Yeah. So yeah, but coming to this thing, what is the conclusion now from this inequality? Mod tau alpha minus alpha is strictly less than mod alpha I minus alpha. So tau is a field isomorphism. So tau alpha will be what? Tau alpha is a conjugate of alpha, no?
It has to be the identity. Tau alpha has to be alpha.
It has to be the identity. That is the conclusion. That's a crucial observation because tau alpha is a conjugate of alpha, and tau alpha minus alpha is strictly less than alpha minus alpha I for all the non-trivial conjugates. Therefore, this can be true only if tau alpha is alpha. So tau is fixing alpha. So our conclusion is if tau is an isomorphism, tau is any isomorphism of k beta alpha over k beta, then tau fixes alpha is our conclusion. Therefore, what can you say? Tau fixes alpha.
To extend tau to the algebraic closure, right?
Yeah.
And so then we can say that is a Galois conjugate. Just confirm it.
Yes. Therefore, tau fixes alpha. And what does that mean? Tau is an isomorphism of k beta alpha over k beta. So if tau fixes alpha, then where does alpha belong? Right? What is k beta?
So does it have to, like, is the fixed set only k beta? Can nothing outside k beta not be fixed under tau?
So which is what I wanted to say. I'm taking an isomorphism of this over this. So if you have a finite extension, if you have an extension L over K, if you have an extension L over K, and if you are taking an element from odd L over K, automorphism of L over K, right? If you're taking an automorphism of L over K, and if that fixes something, then that belongs to K, no? That's the meaning, no?
I think, like, the thing which decides is that any isomorphism fixes it. So therefore, alpha must belong to K.
That's what?
Like, any isomorphism which you take must fix it. So I think that is what is being used.
Correct. Tau is an arbitrary isomorphism of k beta alpha over k beta. You are right. Yeah. So I should have stressed that point. You take any arbitrary isomorphism of k beta alpha over k beta, then you are saying that all those isomorphisms fix alpha. Therefore, alpha belongs to k beta. Now it is fine, right?
Yes.
Yeah. So this was arbitrary choice, and then you claim that alpha belongs to, that is fixed by such an isomorphism. So it is fixed by all the isomorphisms of k beta alpha over k beta. So what you are saying is L over K is an extension, and an element of L which is fixed by everything from odd L over K belongs to K. That is fine. So therefore alpha belongs to, therefore tau is identity, and thus alpha belongs to k beta. And this is what we wanted to show, that k alpha is contained in k beta. So the proof is not difficult, but it is subtle. It's not difficult because the only thing that we have used is extension of absolute value is unique. Nothing else is used other than, whatever properties given. The basic properties of ultrametric inequality. Nothing else is used. But still, yeah, it is a subtle proof. It's an important proof and a very important lemma. Here we will see an application. So we are going to do one application and then we will stop. Okay. So let fx be a monic polynomial of degree n. Monic meaning the starting coefficient is 1 from kx, and you factorize it over k bar. So you have got x minus alpha I power ri in k bar. Fix an algebraic closure. Over that you have factorized it, and consider another monic polynomial of the same degree. Okay, degree is n. So f has degree n and g also has degree n. And we have this notation mod g, maximum of the modulus of the coefficients, right? K has this absolute value. All the coefficients you take the absolute value, and the maximum you call mod g. And that behaves like a norm, right? That's actually a norm on the set of polynomials. And with respect to now notice that if beta is a root of g, then what can you say? So beta is a root of g, meaning beta power n plus etc. plus this is 0. So beta power n is minus of this whole thing. And this much if you take, and if you take modulus, that is less than or equal to maximum of mod Cj beta j. Agree? Because of ultrametric inequality. And so on one side you have beta power n, and on the other side you have maximum of mod Ci beta I. So there is some j such that this is the maximum. So if beta is a root, then you are getting that mod beta power n is less than or equal to mod Cj beta power j for some j, because it's a root from this equation. In other words, mod beta power n minus j is less than or equal to mod Cj. So the conclusion is, if mod g is small, so this is some kind of measure of the polynomial, height of a polynomial, let us say. So if the polynomial has small height, then its roots are also small. That's the conclusion. If the coefficients are small, then the roots are also small. That is an observation. So if mod g is bounded, then the absolute values of the roots of g are also bounded. In fact, a bound for mod g gives a bound for the absolute value of the roots. Okay, so keep this observation in mind. And now suppose g comes close to f. What does that mean? Mod g minus f is small. Mod f minus g is small enough. Then we say that g comes close to f. Suppose in this distance, mod f minus g is small. And suppose beta is the root of g. Then you are going to claim that, so if beta is the root of g, then f beta minus g beta is, so g beta is 0. So this is same as mod f beta. And we are going to claim that mod f beta is small. So if mod f minus g is small, then the claim is that mod f beta is small. Why is that? So we are going to claim that if mod f minus g is very small, then mod f beta minus g beta is also very small. And that is because if mod f minus g is small, then mod g is bounded. Why is that? Because mod g is mod g minus f plus f. Mod g minus f plus g is g minus f plus f. So mod g is less than or equal to maximum of mod g minus f and mod f. So this is, so if this is very small, this is bounded by mod f. Right? So this is, f is a given polynomial. So there is some mod f is some constant. So this is bounded by that. And which implies mod beta is bounded. Why? Because beta is a root of g. So from the previous slide, if mod g is bounded, then mod beta is bounded. And if mod beta is bounded, then mod f, so this is mod f minus g of beta. So if mod beta is bounded, then mod f minus g of beta is small. Why is that? Because f minus g is some polynomial, and f minus g of beta, if you expand, you have summation ci beta power I, and mod beta is bounded, and mod f minus g is small. So ci's are smaller and smaller, and beta is bounded. Therefore, this will be small. Right? Usual inequalities. So this, when you expand, so this will be summation ci beta power I, and ci's are getting smaller and smaller because mod f minus g is small. So ci is small and beta is bounded. Therefore, this is small. This can be made arbitrarily small if this is arbitrarily small. So that was the claim, no? So this is small, but this is same as mod f beta. So this is the argument for this y. Okay, so this is another observation. So if beta is a root of g, then mod f beta is small. If beta is a root of g, then mod f beta is small under the assumption mod f minus g is small. Okay, that's okay. So now you have this factorization, right? F beta had this factorization in k bar. F beta had this factorization in k bar. So f beta is beta minus alpha I power I ri product. So f beta is this. And we have concluded that mod f beta is small. So if mod f beta is small, what can you say from this product? At least one of the mod beta minus alpha I should be small. So that follows from this product that at least one mod beta minus alpha I is small. And yeah, so this is the conclusion. So that means by taking mod f minus g small enough, we can ensure that mod beta minus alpha I, right, by taking this sufficiently small, you can make this sufficiently small, and you can make it in particular smaller than all the other alpha j minus alpha I for j not equal to I. Agree with this? So by making the distance between f and g sufficiently small, you can make sure that one of this is sufficiently small, and that sufficiently small is small enough so that it is less than these other distances. Now this is a Krasnodar lemma hypothesis kind of a condition. So you are going to have an application of Krasnodar's lemma based on this observation. Okay. So now in such a situation, there's a definition. We say that, so if beta has the property that beta minus alpha is strictly less than alpha j minus alpha I modulus for all other j, we say that beta belongs to alpha I. Beta belongs to alpha I if the distance between beta and alpha I is strictly less than the distance between all the roots, alpha I and all the other roots. Then beta belongs to alpha I. And here is an exercise. It's very easy. If you can't do it, look at Lang. Lang gives a proof. If G is sufficiently close to F, then the number of roots of G counted with multiplicity which belong to a given root alpha of F. So this is the definition of belonging to a root. Beta belongs to alpha I. So number of roots of G which belong to a root alpha of F. How many roots belong to a root? So fix a root alpha of F and ask the question, if G is sufficiently close to F, how many roots of G belong to alpha? And that is exactly the multiplicity of alpha. So if alpha has a certain multiplicity, number of roots which belong to alpha when G is sufficiently close to F, that is the same multiplicity. So you can give a proof of that, assume that. And now here is the application. Suppose f is a monic polynomial, f is also irreducible. So up to now we haven't assumed f is irreducible. Assume f is irreducible. Also assume f is separable. Separable means what? Distinct roots. So moreover it has distinct roots. And suppose g is monic of the same degree. Degree of g equal to degree of f. And g is also monic. I'm not assuming g is irreducible. I'm not assuming g is separable. Okay, the only assumption on G is it is monic, the degree is same as degree of F, and assume it is sufficiently close to F, meaning mod F minus G is small enough. And then the claim is, then by this exercise, you know that if it is sufficiently close, then the number of roots belonging to alpha is the multiplicity of alpha, but multiplicity of alpha is now 1 because it has distinct roots. Therefore, number of roots of G belonging to alpha is 1 by this exercise. So roots of G, all the roots will have multiplicity 1 and they will belong to the distinct roots of F, again by this exercise. So each root of G will belong to exactly one root of alpha. So G is also separable and the roots of G belong to the distinct roots of F. This is from this exercise. Okay, by the above exercise. So where are we now? F is given to be monic irreducible, separable, and G has same degree. It is also monic and it is coming sufficiently close. So we can claim that G is also separable, and each root of G belongs to one root of F. This much is concluded. So if beta is a root of G belonging to alpha, then we get K alpha is contained in K beta. Why is that? By the definition of beta belonging to alpha, right? Beta belonging to alpha implies mod beta minus alpha is less than mod alpha I minus alpha for each conjugate alpha I. So Krasnodar lemma applies. Krasnodar lemma applies and you get K alpha is contained in K beta by Krasnodar lemma. Okay. But what is the situation? What is the minimal polynomial of alpha?
F. F.
F, yeah, a bit louder. Yeah, F. F is the minimal polynomial alpha because F is irreducible, monic, etc. So the degree of K alpha over K is what? So all this contains K. Degree of K alpha over K is degree of F. Degree of F. And this is containing K alpha. And what can you say about the minimal polynomial of beta?
Divides G.
Divides G. But degree of G is same as degree of F. Therefore, from this containment, you can say that this is an equality, right? Degree of F is this degree,
Yes.
and this is something which is less than the degree of G, which is equal to degree of F. So some sandwiching happens. So this is actually an equality. So this is degree of F, and since F and G have the same degree, you get K alpha equal to K beta. Moreover, you can conclude something more, no? Not only that, what else have you concluded? So this degree is the degree of G. So the minimal polynomial of beta will divide, minimal polynomial of beta will divide degree of G
It will divide G and also have the same degree as G.
Correct,
So
correct.
it is G.
The minimal polynomial of beta divides G and it has the same degree as G because it's a degree of F. Therefore, the conclusion is G is the minimal polynomial. In particular, G is irreducible. Okay, so it's a beautiful application of Krasnodar's lemma that if F is monic, irreducible, separable, and if G is sufficiently close to F, then you can conclude that G is also irreducible. So it shows you the power of Krasnodar's lemma. So once again, what we have proved is if F is monic, irreducible, separable, and if G is monic of the same degree, and if G is sufficiently close to F, then G is irreducible. Irreducibility comes for free. Okay, so that's a good place to stop. So let me stop the screen sharing. So what do you see now?
What exactly is sufficiently close?
Sufficiently close, no given any epsilon. I mean, you want to make the distance smaller and smaller. So it depends on.
But if I have two polynomials F and G, then how do I check whether they are sufficiently close or not? I don't think it's possible to check.
No, so when we want to, so there will be more precise things to come. So what will happen is we will see. So you could have asked the same question earlier also, no? When I said a unit has an mth root, there sufficiently close was u minus 1 should be less than mod m square, right? So
Yes.
similarly, so here also so what all we are trying to show is beyond a point, if you can bring it down depending on the situation. So we will see, we will put some so what you are asking in some sense is for some effectiveness which is not there right now. I'm not saying look, if mod f minus g is less than this epsilon, then I can conclude this. So that is not part of this. If you look at the arguments, so once again let me share. You can see the screen again, no?
Yes.
So if you look at the arguments, all these arguments are that, see, if I can make this less than epsilon, then so if let's come here. For example, here, for example, at this stage, what are we concluding? If you analyze this thing, so if you give me an epsilon, I can make this less than that, provided I know that this is arbitrarily small. So that may be some other epsilon, that may be some delta. So by making this small enough, I can make this small. That's what we are concluding here. Agree?
Yeah.
Because some other things are involved, some mod beta is involved. So if there was an epsilon, then it's like epsilon by mod beta or some such thing that you need here. Okay, so that is the spirit in which these arguments go, and then you are assuming it here. Therefore, this also you can make this small enough. So you can make this small by making this correspondingly small. That's what you are saying here, and that's what is leading to this definition. So if you can make it small enough, what you are saying is, so what is mod f minus g? Mod f minus g depends on what? It depends on, so f is some polynomial, summation ci x power I, g is some polynomial, summation di x power I, right? So mod f minus g is the polynomial summation ci minus di x power I. So mod f minus g is small means what? Mod ci minus di is small. Right? So
yes.
what you're saying is so if you have a polynomial, so if you come to the very last theorem that we have proved, what it says is given a monic irreducible separable polynomial f, and suppose you have a polynomial of the same degree monic whose coefficients are very near to the coefficients of f. Now you are asking me how near. I'm not saying that because it's not an effective result that we have shown right now.
Okay.
Well, in some sense it is effective, but then it requires more information. To make it effective, you need to know the roots. See, given a polynomial, we have no idea about the roots right there, no?
Yeah, I thought we were doing some sort of irreducibility test, but it's not that, right?
Say that again.
I thought we were getting to some sort of irreducibility test.
It is
but
that.
It is not there right now.
Well, we are there or we are not there, depending on how you want to say. This is Manav, no? So we are not there. I agree with you in the sense that we don't have an effective thing. But this can be made effective, no? Suppose, we are actually dealing with two given polynomials. I mean, you can see that this can be made effective, right? Suppose, you can say something about the roots. Then that sufficiently close can be made precise, no?
Yes, we need to know like a lot of stuff about the roots of f.
Yes, you need to know about the roots of f. Yes.
Okay.
If you happen to know about the roots of f, that is sufficiently small. It's in terms of the roots of f.
Yeah.
So now you know the ingenuity lies in C. You want to say that some polynomial g is irreducible, right? There is nothing, no f in the picture. So you can take an f whose roots you know, no? You can take f such that f is x minus alpha I product, no?
Yeah. Okay.
So yeah, there's a lot of space for various play that you can do. So number theory will be full of such things, Manav. I mean, I must have done Hensel's lemma. I must have given one example, but there are all kinds of questions that one can ask, and one will have to really dirty one's hands by checking examples.
Okay.
So for example, you can take everywhere. I mean, it's not like everything is so precise. There will always be some loose end, and that's where the power of number theory lies. That loose end you can tie. Because choice is entirely yours. For example, in this case, to say something about G, choice of f is in your hand. When we wanted to say that the unit U has an mth root, there was some choice in your hand. In that case, you chose 1 and gave a condition in terms of 1. Right? Mod U minus 1 is less than mod m square. There's nothing specific about 1, no.
And we still have a choice of m, right? Like we can choose an m such that.
Yes. So there are so many choices. You can choose an m and you can choose an m that is correct, and after that also that need not be the condition. Suppose mod u minus 1 is not less than mod m square for whatever m. Instead of 1 you can use another element and try something else. That choice is still yours.
Yeah.
So we are giving this small corollaries which are by no means exhaustive. And these corollaries are useful because maybe textbook authors realize that these are the most useful applications. But that's not the end of it. So there's so much that one can do, and it's in that spirit the sufficiently small comes. It's in terms of making it effective, it's in terms of the roots of f. Roots of f only, no, not roots of g, right? Yeah, roots of f. Because mod beta minus alpha is less than mod alpha I minus alpha, and all these alpha i's are roots of f. Yes, it's in terms of roots of f. Whose choice is yours?
Okay.
Okay, I will stop recording, and if you have further questions, you can still ask. I will wait here.